How are you? Welcome to this lecture, Advanced Thermodynamics and Statistical Mechanics and Practice. I think our student saw the syllabus of my lecture. This course is a continuation of the last lecture of last semester. That is the basic thermodynamics and statistical mechanics. I thought everybody knows the first part of my lecture, the basic part. In this first hour, I will review the thermodynamics because everyone forgot. Not everyone forgot. Someone forgot the contents of the thermodynamics. Here is first law of thermodynamics. In this book, Brundel and Brundel used the sign of the first law of thermodynamics. Here is a plus sign. However, in my previous lecture, I used delta U is delta Q minus delta W. The difference is coming from the definition of the work. For example, in here, when I use this minus sign, when gas is in this system is system, and the outside is an heat reservoir or environment, then if the system is doing work to the outside, then that is a positive sign. That is our definition of the sign of the work. In that case, is minus sign is explicitly appear in here. However, if you define the oppositely the sign of the work, then you can use this formula. Anyway, Brundel and Brundel are using this notation. And this is a finite process, some macro process. You have a delta U equal to delta Q. Delta Q is absorbing of heat from the outside, plus delta W. If you absorb some work from the outside, then your internal energy will be increased. In the infinitesimal process, you have a du equal to dq plus or minus dw. For example, in this gas system, you have a work. This gas doing, if you gas push the piston as a force of the F, then your increment of the volume push dx, then your work is F dx. This is doing to the outside. So in here, in Brundel and Brundel definition, minus sign is up here. So here, so dw is minus pdv. So du is dq minus pdv. So here is minus sign is up here, similarly to our definition. Anyway, then this gas is doing some work to the outside, then their internal energy will be decreased. That is first law of thermodynamics is conservation law of the energy. Okay. Then let's see the second law of thermodynamics. Second law of, in previous lecture, in previous page, the first law of thermodynamics was found by the Robert Mayer in around 1945, 45, middle of the. Interestingly, the second law of thermodynamics was found before the first law of thermodynamics. The second law of thermodynamics was found firstly by the Sadi Carnot around 1832. I'm not sure. Around this year. Version of the Sadi Carnot's version of the thermodynamics given will be given in the next page. However, after the Sadi Carnot, middle of the 19th century, many thermodynamic physicists found out the second law by different statement or different version. The well-known version of second law of thermodynamics is here. I give here two versions: Clausius statement or Kelvin statement. Let's consider the Clausius statement of second law of thermodynamics. The definition, the second law is like this: no process is possible whose sole result is the transfer of heat from a cold to hot body. Here is important is a sole process. 우리말로는 단일한 과정, 어떤 단일한 과정을 통해서 차가운 물체에서 뜨거운 물체로 heat은 저절로 전달되지 않는다는 뜻이죠. 그러니까 반대로 얘기하면 the heat is transferred from the hot body to the cold body. That is natural. The opposite is break of the second law of thermodynamics. Okay, that is Clausius' statement. After that, Kelvin also found the second law of thermodynamics, similar to the Clausius. Kelvin's statement is like this: no process is possible whose sole result is the complete version of heat into work. This here is also important, the sole result. In here, you cannot convert by the sole process the Q to the delta W 100%. It is impossible. 그러니까 열을 갖다가 뽑아가지고 그 열만 뽑는 것이 단일한 과정일 경우에 그것을 100% 1로 바꿀 수 없다는 거죠. 그러니까 이제 열은 1로 100% 변할 수가 없다라는 것이 이제 켈빈 스테이트먼트입니다. 우리가 뒤에서 보겠지만 그게 인버스 과정은 가능합니다. 2를 갖다가 100% 열로 바꿀 수는 있습니다. 근데 이제 그거의 역과정인 델타 Q를 델타 W로 어떤 단일한 연력학적인 과정으로 100% 바꿀 수 있는 방법은 없다 하는 것이 Kelvin statement입니다. Okay, this is Kelvin's version of the second law of thermodynamics. So first, Sadi Carnot found the second law, and Clausius and Kelvin improved the version of the second law of thermodynamics. Okay, then let's consider the Carnot's version of the thermodynamics. Carnot actually consider some engine or some cycle. This is Carnot engine or Carnot cycle. Here is x-axis is volume V and y-axis is pressure P, PV diagram. In this process, this is a cyclic process. It is called Carnot cycle, starting from A. Starting from A goes to the state B, following the isothermal line. Here is the solid line is hot temperature isothermal, 그러니까 등온 process. 그러니까 등온 과정으로 이제 A에서 B로 팽창을 하는 거예요. So it is isothermal expansion from A to B. And at the B to C, also the gas is expand. However, in this time, the expansion is adiabatic. Adiabatic expansion. That means 우리말로는 단열 과정, 단열 팽창이죠. 단열 팽창. 여기는 이제 등온 팽창. I think in the last semester we consider the ideal gas expanded from the isothermal process or adiabatic process. So we already learn about that process. Anyway, in AB is isothermal, BC is adiabatic expansion. Then in this from B to C, the temperature will drop to the actually B is T hot, A is also T hot, because A to B is isothermal process. Their temperature is identical. However, in from B to C, they are adiabatic expansion, so their temperature will be dropped. So at the C, the temperature is reached to T low temperature. In here is low temperature. The temperature is dropped. Then in the C to D, they will compressed, following the another isothermal line, isothermal compression. In this time is compression. 우리말로는 이제 등온 압축입니다. 등온 압축이 됩니다. 그러니까 C에서 D로 갈 때는 등온 압축이 되고, 등온이니까 이제 C하고 D로 갈 동안은 온도가 일정해요. 뭐 어떤 온도로 TL로 일정합니다. And the system reach to the D. From the D to A, they follow another adiabatic compression, also another compression. 이건 단열 압축입니다. 단열 압축이 되면 온도가 올라갑니다. 그래서 D from A, they return to the original position of the thermodynamic stage A. So this is a cyclic process, and this is called Carnot cycle, or Carnot. If you make an engine following the Carnot cycle, that is Carnot engine. Carnot cycle is reversible cycle. 가역 과정입니다. 그래서 PV 도표 위에서 이 모든 라인이 다 실선으로 표현되어 있고, 실선으로 표현되어 있다는 것은 프로세스가 진행되는 동안 모든 연력학적인 상태가 잘 정의되어 있는 그런 가역적인 과정이라는 것을 의미합니다. In the last semester, we derive in this Carnot cycle, we derive this relation. The ratio of the QH over QL is equal to TH over TL. The heat ratio is equivalent to the temperature ratio. This is only hold for the Carnot cycle or reversible cycle. Other cycle does not hold this relationship. You can plot this PV diagram to the TS diagram because in the reversible process, we already know dq is TdS. So absorbing heat is proportional to the change of the entropy. So you can easily plot this kind of TS diagram because from A to the B it is isothermal process. So your temperature is TH. And in the adiabatic process from B to C, in the adiabatic means there is no heat transfer, so that means there is no change of entropy. Therefore, the entropy is constant, does not change from B to C. That is fixed SHCl. Then this is adiabatic process. So in this in the PV diagram of the current cycle is represented to the, and the TS diagram is like a square rotating to the clockwise rotation. Same diagram in different variable spaces. Okay. Then we can. This is a picture of the Carnot cycle. Carnot cycle working on the cyclic process. Then they absorb from the hot temperature to the heat, and this engine is doing to the work W, and they send some heat, that is waste heat, to the low heat reservoir, 우리말로는 쓰레기열. So we need a 쓰레기열, waste heat. You have always this is not 0, greater than 0 is means Kelvin's version of the second of thermodynamics. In this kind of engine, you always need waste heat. Therefore, you cannot convert absorbing heat QH to the 100% to the work W. Then we can define this kind of efficiency of the engine or cycle. You are absorbing heat and work of the engine. So we define W over QH is efficiency of the heat engine or heat cycle. Then we use the energy conservation because QH, first law thermodynamics means absorbing heat is converted to the QL plus W. So this is the first law. Then you combine QH over QL equal to TL over TH. Then we can obtain the efficiency of Carnot cycle is given by 1 minus TL over TH. That is always less than 1. This is version of the Carnot's version of the second of thermodynamics. That is called Carnot theorem. Actually, Carnot does not derive this explicit formula. He gave a statement of this engine. This was derived after the Kelvin, by the Kelvin. Anyway, I'm not sure Kelvin or Claudius. One of them will derive this formula. Anyway, the Carnot theorem is like this. Of all the heat engine working between two given temperatures, none is more efficient than a Carnot engine. That means Carnot efficiency of Carnot engine is most efficient. Some other engines efficiency always less than Carnot engine. There is corollary. All reversible engines working between two temperatures have the same efficiency of the Carnot engine. That is, efficiency of a reversible engine is the same of the efficiency of Carnot engine. Okay, I don't show this corollary. I think you already saw the proving of this statement in the last semester. Okay, let's move to the then we can reach to the Clausius theorem. We already observed in the reversible cycle or Carnot cycle we have this relationship. Then you can change this form to the this kind of formula. Right? You can change this formula as T H over QH equal to QL over TL. Then let's change this formula to the actually a system absorbing heat is positive, releasing heat is negative. So we move to the right side to the left side. Then QH over TH minus. I give a minus sign to the here. QL. Then equal to 0. Then this equation is hold for the Carnot cycle, so we write this formula to the like this one. Therefore, we got the this summation equal to 0. Actually, in this Carnot cycle is like a finite cycle. However, if you consider a small infinitesimal cycle in the two heat reservoir, their temperature is very close, and you consider some Carnot cycle in this infinitesimal cyclic process, then this summation will change to this kind of integration, or for the finite reversible cycle also divided by some infinitesimal Carnot cycle, summation of an infinitesimal Carnot cycle. So we always have a for the reversible cyclic process, your integration equal to this this value equal to 0. However, if you have some irreversible process, for example, your process is reversible, but it's in somewhere is irreversible, including some part of the cycle is irreversible. This is reversible. Then Clausius find out for the this kind of any irreversible closed cycle, your integration of this value always less than 0. Equality is only hold for the reversible cycle. This is called Clausius theorem. Clausius first derived this result. This is generalization of the any process. Their value T over dq is integration always less than 0. This is another one of the result of the second law of thermodynamics. Okay, then we for the reversible cycle we have integration equal to 0. So for some cyclic process, this value will be 0. Your integrand always given some any exact differentiation. So we can change dq reversible over t as ds. That is our definition of the thermodynamic entropy, which was defined by Clausius. Then in this definition, for the finite, this is hold for the cyclic process. For the finite process A to B, then this integration gives the entropy difference between two states. This is hold for the reversible process. For the irreversible process, Clausius inequality hold. Then let's consider a cyclic process A to B to B to A. This is cyclic process, but one is irreversible process, one is reversible process. Then because there is a reversible process, your total process is reversible process. So the Clausius inequality is hold. So your integration to A to B, there is no subscript. That means irreversible process, and B to A is follow the reversible process. Then your addition of two integration always less than 0. Then let's move to this one to the on the right side. Then here is your integration range is opposite to this one. So we change. Actually, if we move to the right side, it is integration minus BA T over dq reversible. So we change the integration sign A to B, then it is plus sign. So this is the hold for this inequality relation. Then in the right side is for the A to B to the like this one, A to B, you measure the entropy difference between A and B, that is delta S. So our result is for the finite two state, for the two states, your entropy difference always greater than T over dq for irreversible cycle, not cycle process. So this is always hold. Your entropy difference is always greater than this value. When a system is observing dq, then you have this relationship. For example, in isolated system, you cannot absorbing any heat from the outside, so you have no heat. So dq equal to 0. So your entropy will be greater than 0. This is application of the Clausius inequality to the for the isolated system. That means this is equivalent to the second law of thermodynamics, result of second law of thermodynamics. So we talk about the second law of thermodynamics as the total entropy of the system is always increasing for the isolated system. That is version of the second law of thermodynamics, 카르노스 버전. 다시 말하면 고립계에서 엔트로피는 항상 증가하거나 뭐 변함이 없다라고 말하는 것이 이제 또 다른 연력학 제2법칙의 우리가 이제 결과나 연력학 제2법칙이라고도 부르죠. 이제 그것이 바로 사실 이제 카르노가 처음에 발견한 그런 사실이고, 그것을 우리가 카르노의 연력학 제2법칙이다 이제 이렇게 부르고, 통상적으로 우리가 고립계에서 엔트로피는 항상 증가한다라고 이제 이렇게 얘기하는 법칙이 바로 이 법칙입니다. 그래서 이 법칙은 결국 우리가 앞에서 얘기한 이제 켈빈스 버전 클라우디우스 스테이트먼트의 결과를 갖다가 다시 이제 포멀라이즈 해서 얻은 결과입니다. So we obtained the most important result of the law of thermodynamics, including first law and second law. So we reached to the definition of the entropy, and we have an statement for the increasing of entropy for an isolated system. Okay. So you can apply the result of the law of thermodynamics. Here this shows some application of the law of thermodynamics. This is application to the universe, assuming that the universe can be treated as an isolated system. The first two laws of thermodynamics became first law, because the universe is isolated, so total energy of the universe will be constant. That means conservation of energy laws, result of first law of thermodynamics. And second is total entropy of the universe can only increase. This is result of the second law of thermodynamics. So 우리가 자주 얘기하죠. 그러니까 이제 고립된 우주의 에너지는 변함이 없고 엔트로피는 항상 증가할 것이다. 결과적으로 우주가 평형 상태에 도달하면 엔트로피 변화가 없는 열죽음 상태, 히트데스, 열죽음 상태에 도달할 것이다 라고 하는 것이 바로 이 결과입니다. Let's summarize our result. In the first, we write the first law of thermodynamics like this one or like this one. From the Carnot cycle, we define, for the reversible process, we define the change of heat is defined as the change of the entropy. And for the gas system, your work is given minus PdV. Then we obtain the fundamental law of thermodynamics is given du equal to ds minus pdv. So this is most important starting equation of the thermodynamics. You can change this formula to the other form. Here is entropy is and volume is your independent variable. However, you can change this equation by the Legendre transformation to the different set of the thermodynamic variable. Here, let's summarize. First law is always true. du is dq plus dw, and this is only for reversible change, hold for the reversible change, and also this work is also true for the reversible change, and this is second law of thermodynamics, so this is always true. No, actually this is combination of first law of and second law, and for the irreversible change we always have dq is always less than TDS, and also your work is greater than minus PDV. Okay, this is the end of the my talk in the review of the thermodynamics, and after this this class, you solve some quiz problem in the I class. I'm not sure the I class is working or not. Anyway, let's consider some. If it does not work, let's consider some other works to accomplish this class. Okay, see you later. 돌아갈 수가 있네요. 마지막 포인트가 지금 틀렸죠. 그래서 마지막 포인트가 이제 틀렸는데, 그거는 이제 in generally this is hold, but we have delta q equal to 0. However, let's think of the delta s is a state variable, so state variable can be calculated from the reversible this kind of artificial reversible process, so you can obtain the delta s by this relation. When the gas system follow the reversible process, delta U equal to 0, so delta Q equal to delta W, so P ds equal to minus P dV, so you can obtain ds is even this one, and if this is ideal gas, if this gas is 1 mole, then it's RT, so your T over P is V over R, so R over V, so you can easily obtain this is as a well-known result of the entropy is increased in this pre-expansion. And we obtain these fundamental relations, and from this relationship you can obtain the temperature variable as a derivation of the round U over round S. Actually 1 over T is round S over round U. However, in this is Clausius entropy, thermodynamic entropy, and Boltzmann was defined the entropy as S is K log omega. Omega is some number of states of the system. That means microscopic information. Microscopic information gives the macroscopic entropy. This is a definition of Boltzmann's entropy. Similarly, Gibbs and Shannon derived the entropy as a probability of a system. We will see this relationship in the later part of the lecture. Okay, maybe this is the end of the lecture. So let's see you in the next hour.